Okay, I'm recording.
Okay, thank you. So you have a load here and the generation station. Okay, so if the load is supplying power to the generation station or the grid, okay, so you can say it is the grid. If the load is supplying power to the grid, then the current will go in this direction. Same time, if it is a DC load, then it will need reactive power to supply power to the grid. So the reactive power is managed by voltage. So voltage will go in this direction, current will go in this direction. So in that case, if the directions are changed or if it is a load, then it should be in this direction. So if the direction changed, then the power factor will be negative. Okay. So that's what coming in the next slide. You can see here, load convention. So load convention, so the load supposed to absorb power from the grid. So the current should be coming towards the load. It should be entering the load. Okay. If the current is entering the load, then it is, if the current enters the positive terminal of the circuit, then the real power is positive, reactive power is also positive. If the real power is negative, if P or Q is negative, then real power or active power is delivered. Okay. Same thing for the generator. Generator is supposed to deliver. If it is delivering, then the current should go out of the leave from the generator terminals. If it leaves, then it is positive. If it gets, then it is negative. Okay. If P is positive,
so it doesn't matter if it's like resistor, inductor, no matter what element.
We are not talking about that in detail. Yeah.
So it's any element.
Any element. It can be load, it can be generator. That's it. So we are now focusing on the direction of the current. Yeah. So it may be anything. As long as the current enters or leaves, we can say the reactive power is positive or negative, real power is positive or negative. Real power positive, negative, reactive power positive, negative is very, very important because that is what going to tell us how much reactive power we need to compensate. So inductive reactive power compensation or capacitive reactive power compensation. Right. So this I showed you already. And this is the industrial setup where they have the local reactive power compensation inside the facility. And these are the relationships that we talked already, circuits and other previous courses. When you're talking about RMS voltage, we are talking about Vmax over square root 2. And inductive reactance, capacitive reactance, active power, reactive power, complex power. Yes. Apparent power is usually given by S. Okay. So it can be written in the polar form as P plus JQ. Active power plus reactive power. And in the rectangular form, it is P squared plus Q squared and the square root. So it gives you the magnitude. Okay. Right. So power factor is given by this. Inductive load current lags the voltage. So beta is less than dou. If it is a capacitive load, beta is greater than dou. Okay.
I mean, reading through the text, I understand it, but I just want to make sure. So complex and apparent are just like
same.
Synonymous. Okay.
Synonymous. Correct. Right. So I'll walk through these examples. You can stop me anytime. So this is just the basic example. We are talking about a single phase voltage source with V equal to 100, angle 130. It delivers a current of 100, angle 10. So which leaves the positive terminal of the source. So both are positive. Okay. Calculate the real and reactive power. State whether the source absorbs or delivers the power. Okay. So real and reactive power, we have voltage and the current. So we can calculate the apparent power. So when you are calculating the apparent power, we see S equal to V times I conjugate. Conjugate means whatever the direction you are putting to I, it should be reversed. The complex term of I should be reversed. Positive complex, positive imaginary term should be changed into negative imaginary term. Okay. So we are talking about VI conjugate. So you are getting this as a result of V and I. So when you get S equal to S is usually in the form of P plus JQ. Okay. So when you multiply V and I, you can what is the from the result you can say what is the real power, what is the reactive power. So in this case, the real power is minus 500 and reactive power is plus 866. I mean watt. Okay. So it is a generator, a single phase voltage source. Current leaves the positive terminal of the source, which leaves the positive terminal. But you are getting a real power negative. So what the rule says here, so for the generator convention, if P is positive and Q is positive, positive real power is delivered and positive reactive power is delivered. If P is negative, then positive real power is absorbed. Okay. So here it's a generator. We are talking about negative real power. So power is absorbed by the source. Okay. Whereas reactive power is positive. When reactive power is positive, it is delivered. Okay. So this scenario to synchronous motor, which is operating at leading power factor. Okay. So if it is a leading power factor equipment, then it should absorb the power. Okay, real power. That's the scenario where you compensate it with the inductive load. Because it is automatically working as a leading power factor means capacitor. So it is already providing a capacitive load type of scenario. So that time you have to add inductors to compensate it. Is that the question you wanted to ask? No. Okay, go ahead. Yeah, you read this rules.
Yeah, so in this scenario,
Mm.
if the how do you call it, the real power is positive, then timing is delivered. So if the reactive power is negative, it's absorbed.
Yes. So in general, you have to understand this slide in this way. If you are talking about load, the load in general convention, it should absorb power. So anything if it does opposite to that, means it is delivery. Okay. If when you are talking about generator, it should generate and send out the power, leave the power. Anything it does opposite to that means it's absorbed. That is what it means. Right. So the second example here, we have a source which is delivering 100 kW, load operating at a power factor of 0.8 lagging. Calculate the reactive power to be delivered by the capacitor connected in parallel with the load in order to raise the source power factor to 0.95 lagging. Okay. So this question, so we are talking about a source with 100 kW. Okay, so real power is given. P equal to 100 kW. And the source, we have a source and the inductive load. Okay. So this is P equal to 100 kW with power factor given as 0.8 lagging. So that's why I put here inductive load. So in order to raise the power factor, we have to add capacitive load. Okay, so we are adding it with the capacitor. And this capacitor, so when you draw the power triangle, the normal power triangle is like this. P, Q, apparent power, yes. Okay, V, I conjugate. This is K1, V, I cos dou minus beta. This is V, I KVR, V, I sine dou minus beta. Okay. So now the power factor, what is power factor? Power factor is a cos angle. Okay. So cos dou minus beta. So power factor is cos dou minus beta. So you have this factor here. So this factor Vi is real power. So real power P equal to Vi cos dou minus beta. So this is Vi cos dou minus beta. Real power is given as 100. 100 kW equal to Vi cos dou minus beta. So you can calculate what is Vi from this. 100 divided by 0.8 equal to Vi, apparent power. Okay. So get your Vi. And then cos dou minus beta is given as 0.8. So what is dou minus beta? Cos inverse of 0.8. Now change this cos dou minus beta to 0.95. So this is what for this scenario, the given scenario. Now you want to add a capacitor. So when you add a capacitor, power factor is going to increase. Okay, so this is cos dou minus beta. Adding a capacitor, the power factor is going to increase. So it's going to result in this diagram. This is the original diagram what we have done here. Okay, cos dou minus beta, which is equal to 0.8 QP. Yes. Okay. Now you are adding a capacitor here. So when you add a capacitor, this angle 0.8 should change to 0.95. When it is changing to 0.95, it's going to change from QA to QB. So this is the amount of reactive power you are adding by adding the capacitor, so that your total reactive power can change. This is QT. Okay. Can you understand this problem? What is happening when you change the power factor from 0.8 to 0.9? So you can calculate how much is the angle. So cos dou minus beta is now 0.95. So what is dou minus beta now? Cos inverse of 0.95. So this real power is not going to change. I told you already. Whenever you add something, real power is not going to change. So your real power P equal to Vi cos dou minus beta. Now this cos dou minus beta is 0.95 and this P is 100 kW. You can calculate the new Vi. Calculate the new Vi. So from that new Vi, cos dou minus beta is 0.95. So what is sin dou minus beta? Calculate sin dou minus beta. Now you have Vi, multiply it by sin dou minus beta. You get Q. So this is the old Q and this is the new Q. Okay. So old Q and the new Q. From that you can calculate how much Q you need to add.
Question.
Go ahead. Yeah.
Is there, maybe I missed it. Why did we use 0.95 as a new power factor?
It is given. It is given in the question. First part of the question is how much capacitor connected in parallel to increase the load power factor to 0.95.
Okay.
Yes. So this is what the solution is. Calculate the dou minus beta theta value and calculate the reactive power. The first case. In the total case, this is the first case. This is the second case. Okay. Go through this and you can understand this. And I want to show you this. Let's take this example. Do it in Powerwall, and we will also do the same example in the lab. Okay. We take normal load, add capacitor, and see how the reactive power curve is changing. Okay. Right. So the next one is also similar thing, but here in this problem, real power is given. Okay. Here kVA means apparent power is given. So VI is given, same question, 0.8, 0.95. But when the apparent power is given, how do you calculate the reactive power? It's just translation of the equation. Okay. So you take the apparent power, calculate the power factor, and then from that. So the apparent power 100 kVA can be written like this, 80 plus J60. And from that you can calculate the capacitance that you need to add here. Okay. So take a look at this slide and let me know if you have any questions. So you can calculate the apparent power. You can keep the apparent power 100 kVA and use any of this equation. So this is apparent power is S equal to P plus JQ. That is correct, but I just want to tell you in the other way. S over P. Okay, so you can take the angle here. Okay, cos 0.8 and cos dou minus beta equal to 0.95. Okay, there are two angles are given. So from that angle, you can calculate the division of the two. Like here, you can say calculate. So S equal to P squared plus Q squared. So from that, you can calculate the power factor, the total power factor, P over S. So that is going through equations. Otherwise, what you can do is, S equal to P plus JQ. And S is given as 100. So 100 can be split into, what is S? In the polar form, it is P squared plus Q squared. So this is 100 equal to, what are the factors that can fill here? 80 plus 60. 80 squared plus 60 squared can give you 100. So you can split it in that way by normal math. Or you can go through this S equal to P plus JQ, where P equal to VI cos dou theta, Q is VI sin dou theta. Take VI common out, cos theta plus dou sin theta, perform the trigonometry, and you can get this relationship. Okay. So is this example clear? All right. So this is about the capacitors we talked about, how much capacitance that we are compensating. So the first picture I showed you, there are capacitors in the yard. Those are capacitor banks. And we can also have distribution capacitors which are installed in the distribution lines. They can be switched by the switchboards, okay, by the switches here. Right. So this is third example. Here there are two types of loads. One is an induction motor, which is real power factor is given. There's a synchronous motor, synchronous motor means capacitive load. Okay. So it is having apparent power and the power factor, and the total power is given. What is the total power factor of the combined load? Okay. So what you can do is, you can calculate the apparent power you have to bring both loads into a common term. For one load, it is given as real power, another load is given in the apparent power. So bring both loads in the apparent power terminology. Okay. So when you bring both loads in the apparent power terminology, you can solve them together. Okay. So the first load is given in the apparent power. You bring the first load into induction motor into apparent power. Synchronous motor is apparent power is already given. So in the apparent, after you calculate apparent power, you can calculate the reactive power. Real power is already given. So calculate all the three sides of the power triangle. Same way here, for the synchronous motor, apparent power is given. Calculate the other two sides of the triangle, real power and the reactive power. Now you know everything. You can combine real powers, combine reactive power, put it in the equation to get the apparent power and the power factor. Okay, take a moment to look at this. We'll take a break after finishing this example and one more example. I can see you're all very tired. You definitely need a break.
So P over S equals power factor, right?
Tell me one more time.
According to these formulas, P over S equals the power factor.
P over S equal to power factor. Yes.
Okay.
I think I have given it here. Yes.
And maybe this is a stupid question. Have you posted this? Is this posted on the canvas?
Yes, it is posted on the canvas.
Okay.
Don't worry, no question is a stupid question in this class. Okay, feel free to ask any question, anyone. Okay.
Sounds good. Thank you.
Right. So moving on to the next example, it is similar to the previous examples. We are talking about a delta connected capacitor bank installed in parallel with the combined motor load. How much is the capacitive reactance that you need in each leg? Okay. So total capacitance, the equation should be given here. This data must be given here. Okay. So for unity power factor, how much is the? I think there is a picture missing here. Oh no. This is a continuation of this problem. So here we are talking about the power factor of the combined load, magnitude of the current, line current. Now we want to compensate this power factor by a delta capacitor bank. Then how much it is? So we are taking these values and calculating the capacitance required. Okay. So how much is the reactive power we calculated here? Total reactive power calculated is 234.6. So that's the total reactive power. So this is the formula for the capacitor bank. So from here we can calculate the X value. That's the capacitive reactance. And if once you know capacitive reactance, then X equal to 1 over 2 pi FC. Okay. So then once you know this XC value, you can calculate how much is the frequency it is going to contribute, how much is the capacitance it's going to contribute. Okay. So if you know the frequency, you can calculate capacitance. If you know the capacitance, you can calculate the frequency. Okay. So that's what we are doing here. Calculate the XC value because we know the V value, we know this X delta value. So calculate the X delta is coming from the QC value. Okay. QC is nothing but the reactive power. Calculate that X value and from that you can calculate the current value. So this is the current carried by each phase when you are compensating it with this much of capacitance. And this X can be expanded into this value 1 over 2 pi FC to calculate actual capacitances. How many capacitance that need to be turned on. Okay, that can be done here. So take a moment to look at this and then we can have a break now. My clock reads 2:32. Maybe we will meet at 2:45 and we will start with Power World when we are meeting. Okay. I go quickly to ITS, grab my laptop, come back here. My laptop is ready. That's what I say. Tony, are you not in the ASOIT this year? ASOIT. Last year you were in it. I thought you were in ASOIT. Okay. Alfred, can you see my screen and the screen that I'm sharing? What are you seeing on your end? Yeah, Tom, what are you seeing on your end? So this slide, right? Okay, cool. So do you have your simulator open? All right. So this is these slides are posted as lecture 3. These slides are just the example to be the Power World, one small project in Power World from scratch. Okay. So what are we going to see in this example is the example that we did theoretically. So we have a capacitor, we have a generator, a load, and we are just connecting it through the transmission line, and we are changing the real power to see how much the power the apparent power changes, how much is the real power changes, how much is the reactive power changes in the line when the load changes. This is what we have been talking right from the first lecture, right? So we will see how much it does, and then we will try to add capacitor to this, and then we will move on from there. Okay, so this is the example we are talking about, and there are steps shown here how to build the two bus power system with all the necessary parameters. So what I'm going to do now is I will share the open the Power World, and then I will show you how to do it. You can do it with me parallelly. Okay, I will do step by step, and you can follow, and you can ask me questions if you have any doubts. Okay, right. Okay, so now this is the screen you might be seeing, and we wanted to start a new project. Okay, so before we start the new project, let me explain the screen here. So this is just the general screen. First screen you'll be seeing every time you open Powerwall. Okay, so here there are many toolbars. So this is the toolbar. I mean, first you have to go to File. Oh, here. File, open new case. So when you open new case, you will be opening a new palette. This is where you are going to build the project. Okay. So here, in this, we have to bring the components, right? There is generator, buses, loads, transmission lines, and distribution lines, everything. So for that, you have to look for draw. Go to draw here. When you put, press this network down, you will see all the components listed here. Okay. So the first and foremost thing you have to bring here is buses. So you have to have the buses or feeders to which we can connect everything. Okay. So bring a bus. First, bring a bus. Okay. When you click bus and bring it here to the empty screen, you will see this. So here you can just drag this. When you click it on the empty screen, it will ask for the bus details. So look at the bus details. What it is asking, it is bus number and how much is the voltage it needs. Okay. So we can give here like 16 kV. Change it to 16 kV. Right. So plus enter, and then orientation, bus information, you can say here, what is the voltage per unit and what is the angle? Okay. I will come to this place little later. Okay. You can leave it as it is. Now display. How do you want to draw this bus? You want to draw it horizontally or vertically? Accordingly, you can choose here. So I want to draw it horizontally. So I'm choosing right. Okay. And then attached devices. You can say what are the devices that you are going to attach to it. Is a load or capacitor or anything. You can leave it for now. Okay, you don't need to do anything. We will add components by components so that you know how to add components, and then we can see how we can modify it with the bus. Okay. Geography is actually talking about where this bus is located. In reality, you can specify the location of this bus so that when any fault happens, your system can pick it up. And this is the bus which is located in this area is what is at fault. You can give the name, like this bus is located in Wilsonville, so Wilsonville bus. Then it will show you like Wilsonville bus is affected, so like that. Okay, so you can give the name, you can give the latitude, longitude, so that it can pick up exactly in which location in Wilsonville or how far from Wilsonville there is a fault. If there is a line drop, it can locate from how far from that location the bus line fault is happening. So location is important. We are not going to do anything about the location now, but I'm just explaining you. Okay. So the custom is a float. So what are the float? Float means it's a floating devices. Is there any inductors you are going to add, capacitors you are going to add? Is there any local generators or battery banks or anything, that kind of things that you can add? Okay. So that is what it's talking about. And stability. Stability is actually talking about stability is this column is required for balancing the voltage and frequency. When you are balancing the voltage and frequency, you have to look for it. But for now, for the bus, it will not show any stability because bus stability is dependent on the component which is connected to it. If you are connecting a load, then you have to look at the load stability to look at the bus stability. If the bus is connected to the generator, then you have to look at the generator to look at the bus stability. So actually, for the bus, you will not see anything. Your question. That's what. Oh, good.
That's why we don't have this stability.
Here. And here you are seeing the area. So when it comes to protection, we have to name the areas and zones because protection is usually happening in terms of zones, and the zones must be overlapping. So to overlap the zones, you have to name the zones. Like you can have zone 1. So if this is your one line diagram, generator is connected and load is connected. Okay. So if this is your one line diagram, this is with bus 1, bus 2. Okay. This is generator, load 1, load 2. So if this is your one line diagram of any network, then you have to zone them. Zoning, I'm not going to go in detail with zoning, how to do the zoning now because we'll be talking about that in detail in protection class. But just to give you an idea about that word, okay? So when you are connecting a zone, you will be connecting it like this. This is zone 1, okay? So zones are actually named from the buses. How many buses are there? That many zones must be there physically. Okay. So this is zone 1 and this is zone 2. So we usually say buses are usually connected to transformers. So we usually name it based on the transformers. Okay. So this is zone 1, zone 2. But I said the basic fundamental rule for protection is zones must be overlapping. So you have to have another zone which is covering zone 1 and zone 2. So this red one, zone 1 covers this bus 1 with the generator. Zone 2 is covering the loads with this bus 2. Whereas zone 3, overlapping zone, is covering the 2 buses. Okay. So this is how zones are categorized in order to make the protection perfect, so that the protection is not failed anywhere. Okay. So that is what the zones are referring here. This word zone here, you have to name each bus by its zone so that you can overlap it later. Okay. So that is what we are doing. And we can say who is the owner for that bus. So this bus may be belonging to PG. That bus may be belonging to uh, Pacific Card. So you have to name it so that you can know whose bus is getting overloaded, which bus is turning red, which bus is turning green, so that money can flow accordingly. Okay. And you can say if there is a substation present, you can say the substation name. Uh, it's a BPA substation or what, a Pearl substation, like that. And who is the data maintainer? So the person who is designing this, who is going to collect the data, that name needs to go here. Okay. So these are the things, and we are not going to worry about all these things right now. When you are including the bus, you just need this voltage, bus voltage. Okay. So how much is the capacity of the bus? That is what we need to do. But these are the other items that you need to know what is the meaning of it. Okay. So once you put the bus capacity, then nominal voltage, click OK. You will get the bus like this. And you can just drag it, and you can click on the number and bring it wherever you want.
So they are all one.
Come again?
We put one for all of them.
Bus.
The area is one.
Yeah, leave it default.
Oh, okay.
So when you click on the number, double click on the number, it will open up another window like this. So here you can change the values, like the size of the number, everything. You can also give here bus name or bus number. You can give bus voltage in per unit or bus voltage in kVs. Okay. Whatever you want to see in that one line diagram related to the bus, you can just select it accordingly.
Did you say the first unit bus voltage was?
16 kV
No, what's PU?
per unit.
Oh, just per unit.
Per unit. So you can also select, I mean, if you want to see how much is the money flowing across the buses, you can do that. Okay. But for this class, we need to see, we are not looking at the cost, we are looking at all the sides. Okay. Just click OK. You can see it is showing up. When you drag it, you can see it as a bigger picture. So this is a 16 kV bus. Double click, open the bus, and see you put 16 in the as the value. Okay, double click the number 1, open it. Will you do that?
Yeah. And that's it.
Go to bus voltage. No, next one. Yes. Okay. Right. So So now we want another bus, right? So you can either copy paste this bus or you can just bring another one. Control C, copy objects and records. And then Control V. Create new object. Okay, don't link it to the existing one. If you link it to the existing one, whatever changes you do, it will reflect in the other one. Okay, so you can just drag it and place it here. Okay, so I think I'm seeing a difficulty here. Showing 16 kV. Okay, are you seeing the same thing? I understand. I think that is coming from here. Okay, change the. Look at this bus. The second bus may be having an issue. Second bus is also 16 kV. Good. Okay, so this is bus number 1, and this is bus number 2.
Bus 2 is the same TV fixture.
Yeah. So here, bus voltage is taking it as bus name. Click OK. Right, it is changing now to 1. Okay, I think I'm having trouble creating this. Double click, open the bus and put it as 16 kV, and then voltage per unit you can change it to 0.98 and the angle minus 1 point. Oh no, you can leave it as 1 and 0, not a problem. Like before, you can leave it as it is.
It'll change once you run it, right?
Yeah, 0 0. Okay. Control C, Control V. Create new object. Double click, open. Okay, leave it as bus number and then we will see later. Hmm. All right. Now, let's bring the transmission line, connect it between the two buses. Transmission line. I think I need transmission line parameters. Huh? Give me a second. I will come. I will come.
I'm not able to get them to
Is that read the same bus?
Yeah.
Oh, is it okay?
You can control and paste.
that's what I did there.
We're just trying to get display the name.
This is this is
Oh, you can see that.
So transmission line, when you're drawing transmission line, click here one time. Click on one bus. Click wherever you want to take a branch. I mean, take a turn. And then end it here. So when you click one time, you have to click double time. When you click double time, it will open up a panel. Here you will have to fill up lot of information. Do you need me?
Now you have two separate ones. Two distinct ones. Yeah, okay.
Right. For transmission line, actually, these things are very, very important. Series resistance, because it's a transmission line, we need to specify what is the type of the cable, how much is the inductance, how much is the resistance, and everything. Okay. So let's put these values here first. 0.3, 0.6, and Rx, GB. So we can leave that as 0 and 0. And then what else? Parameters. Here you can, the other thing, stability geography is the same. Owner area zones are the same. Here for the transmission line, we get new tab, fault info. So later when we are talking about the faults, we can say, we will talk about the zero sequence, positive sequence, negative sequence components. So we got a zero sequence is related to the ground. How much is the ground impedance we are going to add to the system? Because it matters when we are talking about the fault, the ground value is very, very important. If the ground is of higher impedance than the line, then the fault is not going to go through the ground because it is giving lot of opposition. So that it cannot take the fault. Ground must be at a lower impedance than the line. Then only if any fault happens, it can go through the ground. So we always provide a metal rod at the ground and provide it with a wire and connect it so that the wire and the rod can provide a lower impedance path for the current to flow, fault current to flow through it. Okay. So how much is the impedance that metal and the wire together is providing the ground, the metal and the wire which are connected to the ground? What is the impedance of that? That is what it's asking here. RC and the capacitance. Why we are talking about the capacitance here? Because the grounds, if you are, if you are laying out the transmission lines, if this is the tower, then the ground lines will be flowing from the top wire to the tower, ground. Okay. So there will be a capacitance between the ground and the top wire. So this is C. Okay. So this C is they are asking about. That is based on how tall the tower is. If it's a distribution line, then the tower will be shorter. Capacitance will be, because capacitance is given by C equal to epsilon R B over A. So area is coming from the area of the capacitance. If you have two charge plates separated by distance, what is the area, total area? And D is the distance between the two plates. So here the top plate is this, bottom plate is this. ground is charged. This top wire is also charged. So what is the distance between the two? So that is what the D is talking about in the capacitance. So that's why we need to see the capacitance value and put that value here when you're talking about the capacitance, when you're talking about the ground wire. Okay. And also between the two wires, there will be a capacitance form. So when you are laying out the parallel lines, also you need to calculate the capacitance between the two wires, because when you are talking about the parallel wires, then the wires will be flowing like this. So there will be capacitance between this C1 and C2. Because this is a charged wire, this is a charged wire, the distance between the two one will form C1. This is another charged wire, this is another charged wire, the distance between the two will be C2. So we have to calculate that capacitance and put it here. Okay. Line to line. Line to ground. Correct. Okay. So so that is a zero sequence. Zero sequence indicates the ground. Okay. So it is very important to look at the ground values when you are talking about faults. We are not looking at the line to line capacitances. We are looking at the ground wire capacitance and the ground wire details, because they are contributing to the ground faults. Most of the faults, 70% of the faults happens as single line to ground. Only one line will come to ground. Okay, so 70% of the fault. The highest fault, the heavy current fault, is the 3-wire fault. The lowest current is a single wire fault, but that is what the common fault is. So that's why we are looking at the ground wire details here. Okay. And then fault info, we are talking about all the ground and neutral stuff. And then series capacitor. So if you are connecting, I showed you a picture where the tower is connected with the capacitor, right? So if you are connecting a capacitor in the tower, then that capacitance value can go here. Okay? And then if your line is connected, your bus is connected with the transformers, then you can put the transformer details here. Okay. And yeah, so we are not going to put all these things. We will add all those things little by later. Okay. So this is the first thing. Just try to give OK. You will get this line connected. Okay. So you are seeing a small little red block here at the end of each line, closer to the buses. They are circuit breakers. Okay. So whenever you put any component to the bus, it will come with circuit breakers automatically. And if you double click that block, you can open the circuit breaker. You can open the circuit breaker. It will show like this. If you double click open, cancel. Cancel, sorry.
And what is the cycle in between the
I will come to that right now. Yeah. Before that, let me take your question.
Before I get rid of this.
This is why I said in your verification. So where is your... So when you're taking the line,
I usually do this with maps so that doesn't happen.
yeah. So you will have to click one time here,
Okay.
and then drag it. You will get it. When you're coming to the end, here, click double time. You will get this. Right. Now this, the blue bubble here is what showing you how much is the line parameter when it is running, when the whole system is running, what's the line capacity. So now it is, you can double click open, you can see. So what you want to see in the line? 0.3 and 0.6. So when you double click open this, you can see, you can select what you want to see. You want to see the apparent power or real power or reactive power. You can select whatever you want, or you want to see the current. Most of the time we will see the current, because the line current is very, very important. That's what we observe in our real time, because the line current is what going to tell us about the fault information. If the current is swelling too much, then there is a fault. If the current is normal, then there is no fault. So we select line ampere and transfer MVA. Transfer MVA is how much apparent power is transferred from line bus 1 to bus 2. Okay, so we can see all those informations here. It will show as blue when you are connecting it, but when you are running it, it will change its color. Okay, right. Tell me when you are done with this step, I will show you. The next step is to connect generator and load, then we can run the simulation. Are you all done with this? Okay. Now, next thing is generator. Go back here, select generator and click here. Just click it in the empty space. It will open up the palette here. So, this is asking for the power. Okay, megawatt set power. You can say 5. So minimum output power, maximum output power, you can just leave it as it is. So the participation factor is actually, this information is, have you finished putting all these things here? 5, just only one value, megawatts at 0.5. Okay. So now I'm talking about this thing here, participation factor. So what it means is, in the generation or in the substation, if you have a generator, then we have to specify how much percentage of power we are taking from this generator. Imagine the first lecture I showed you how the generator and the loads are located. And I am talking about the power demand, the power supply and the demand. I showed you a picture looking like this. So this I see conventional generator, thermal. This is maybe hydro. So generator G1, G2, G3. Okay. So this is actually filling the tank. And here, this side we are having loads. Maybe residential load. Industrial load. Commercial load. Okay. So when you are connecting more than one generator to the system, we are not going to take all the power from the conventional generator or thermal generator or any other generators. We have to specify to run all these loads, how much percentage of power you need from this, and from this. Because we have to utilize all the generators also. Because starting a generator from scratch is a costly process and it takes time. So we cannot let any generator to stop completely, because that is what we call it as black start. There are so many words related to start, black start, brown start, all those things. Okay, so when you have to run all the generators parallelly, but some costliest generators, oil and gas generators, we can take more power, and less cost, we can take more power, more cost, we can take less power. So how much participation factor each generators are having to this grid to supply these loads. That is what the participation factor we are saying. Suppose I say in terms of numbers, if I say the generator capacity is 10 megawatt and I put participation factor as 10, it's going to take only 10% of 10 megawatt and supply it to the grid. So whenever you add more loads to this diagram, and the generator, even though it is having a full capacity to supply all the loads, and you put only 10%, then it's going to take only 10% from that. Then it will run out of generation. That is what it means. Okay. Generation factor is important. And then here available for AGC. AGC means automatic gain control. If you check this part, then if the generator need to increase its capacity, then it will do it automatically within that value. Okay. And then AVR. AVR is for reactive power, automatic reactive power control. It will also adjust the reactive power automatically within a range, not to the entire scenario. Okay. Enforce MWO limits during automatic control. Meaning what? When it is doing the automatic control, you should make sure that the real power is within that range. When you are supplying the more reactive power, it should not drop the real power. That is what it means. Okay. So we usually keep it as checked. Okay. Capability curve. So the capability curve, I'll show you the curves when you are analyzing the results. Okay. So there is a capability curve and you can use the capability curve to determine all these points. So when you check this one, this all will be working based on the curve, not from the points. Okay. That is what it means. So now let's put the values here. Keep the MW as 5 and then M bar as 0. Maybe you can keep M bar as 1. Click OK. And then this one actually drag and attach it to the line. Okay. You can double click open the generator, power and voltage control. You can change this M bar output as 5. Okay, done. Oh, it will not. You can just drag and drop it near the bus. It will be connected when you are running it.
I'm sorry, I was going off with the PDF for the instructions for this lecture. The participation factor is 0, and I missed the part where you concluded on that. Did you end up taking 0, or did you leave it?
No, I just left it as 10.
Okay, I got you.
Excuse me.
Mm.
Yeah, I think
Where are you now? Is the canvas working now?
Oh, no, I downloaded
You
it.
downloaded it.
Yeah.
Okay. Yes, your question.
yeah, I'm trying to connect.
Just drag and drop.
Yeah, look about it.
Yeah, that's correct.
Yeah.
Oh, the transmission line.
Yeah.
So, take the transmission line. No, you haven't selected the transmission line. Click one. Click one. Now drag. Click. Yeah. Make it straight. Yeah. Make this one 0.3, this one 0.6. All right. So now the next thing is load. Go back, take load. Double click. Put the M watt as 5. M watt as 5. Because load and the source must be balanced. Supply and demand must be balanced. So let's put it like this. And now you can connect it. Hmm? Yeah, you can change it to 5. Or you can leave it to 1 and see what happens. I mean, I'm going to show it anyhow because we have to explore everything, all scenarios. Right. So I just put these values and you're good. Now we are done with our diagram. So when you're ready at this stage, just let me know. I'll show you how to run the simulation.
This button display the load values.
So whatever you're putting here as M watt and M watt, it will be displayed. And you can also choose what you want to see, but I will tell you that one a little later. Are you not seeing this numbers?
No.
Double click, open the load. Oh, okay. So wait. You have to put the load. Yeah. Okay. Double click open. Double click open. No. Click OK. And
It's fine.
no, it is not. I don't want to look at that. Wait. Let me just look at mine. I think my version is a little different. Okay. Load information. And can you walk around here? Is there anything display information is off track for you?
It's all this. I just got it all matched.
Mm-hmm.
Oh,
You found it?
yeah. I had to zoom out a little bit. It was
Okay.
weird.
Oh, when you drag it from that direction to here. Okay, got it. Ready? Now? Done? Xenon. Are you?
Yeah, I'm not getting the 5 together.
Okay, that's same issue. Okay, so. Okay.
Yeah, just zooming out if you can find it.
Oh, it's right.
Yeah, that's the same issue.
Yeah. Well done. Okay, right. Now put it in on the left hand side here. Alfred, are you okay? Have you done until this step? I didn't check with you.
I missed some of the parts. I'll have to watch the video again. So
Okay. Right. So put it in run mode. Okay. So here you can see that now we are in the edit mode. If you want to change anything in this diagram, you have to come back to edit mode. If you want to add components, change fields, do anything on this diagram is in the run edit mode. Okay. When you want to run, then you have to put it in the run mode. Once you put it in the run mode, you cannot change anything. Okay. You can just view it. You cannot change anything. Now, after you put it in the run mode, you can see here the network, all these things will go gray, meaning you cannot change anything. Okay. Now go to tools. Under tools, you are seeing a green button. That's the run button. Okay. So just click this run button. You will see the power is flowing through this. Okay. So we made the power to flow through the lines. Now we have to look at the line of what is the values that it is carrying. Okay, so you have to go here, case information. Model Explorer. It will open up a table like this. And this table will tell you based on the number of buses. Bus 1, what's the per unit value of voltage? What is the kV voltage? And what is the angle? And how much is the generated power? MVAR, MVA, everything. And the load. Okay. So this is the first level of looking at the solution. You can also look at the generators here. So we have only one generator in this diagram. You can also look at the load. And you can look at the mismatch, supply and demand. What is the mismatch happening here? You can look at the mismatch. So one is slack, one is PQ, there is no mismatch. You can see load in the source. One is connected to bus 1, generator is connected to bus 1, load is connected to bus 2. So it looks for the mismatch in the buses, not the equipment. Okay, mismatch between bus 1 and bus 2, there is no mismatch because we connected it properly. We generated 5 kVA, 5 kW, and the load is 5 kW, so it is actually working together. So we are not seeing any mismatch here. Okay. So now you can play around with this. Go to buses. Here you can see a lot of information. What's the area zone? What is the AGC? Is it doing any automatic gain control to match the load? All those informations you can see here. Okay, so I'm going to stop it here because I don't want to load you with too much information in the first day itself. So this is how we have to build the basic diagram and then look for the solution. Okay. So the next class, next week, we will add one more, maybe one more bus or one more transmission line. And then I will take you to the further analysis, like what are the further analysis you can do here. Okay. How to observe other results. Okay. So this is a fundamental way of building a one-line diagram, very simple diagram, and how to look for the results. Okay. Right. So I'm going to stop here, open the floor for questions, and we still have one discussion to carry on. Are you all ready? I think can we have the discussion next week because I don't see other online folks. Or if you are ready, I'm ready to listen.
Let's do it next week. I don't mind doing it next week.
And that's the Texas blackout.
Texas blackout, right?
That's the February 21.
Correct. That's the major blackout happened recently. Yeah. Right. So we will have that discussion next week. Not a problem. Right. And then we finish this first part. So can we go for quiz next week? So we will have quiz 1 next week. Next week, Monday, same time. Beginning of the class. And you can tell me you want to take the quiz by Zoom, I mean lockdown browser or paper based, so that I can print out the question paper. How do you want to take? I mean, online students are going to take it in lockdown browser. So it's your preference.
Multiple choice.
It is quiz 1 is based on the lectures, what we saw until today. Go for the practice quizzes and you can take the practice, and it's mostly based on the practice quizzes.
So in class, you take it in lockdown too?
Yes.
Oh,
You don't like it?
oh no, I'm okay.
All right.
I'd be in favor of a printed quiz for in class.
Okay.
So if we take lockdown in class and there is a noise around, do that?
I can disable that feature.
Oh, okay.
That's why I was asking. Uh-huh. So, how many of you? I mean, there are only 4 people. If you vote, then it will become like equal votes. So, I cannot let the class, somebody take lockdown process, some other people take paper based. So we have to come to a common conclusion. So let me ask this question, formality question. How many of you want to go for paper based? How many of you don't raise your hand without
The answer is yes. Let's do it.
paper based?
No, paper-based demos.
You lost it.
Oh, I'm okay.
Yeah, okay, good. Then okay, fine. Classroom is paper based. Other students take it a lockdown browser. 1 to 1:30 next week Monday. Based on whatever we talked just now. Reactive power, only theory. Okay. Practice quiz will help you to go through the theory and also look at the textbook. Right. So if we are not doing any discussion today, I think I am done for today. You can ask your questions. Yes.
You said you're gonna extend the homework
Yes.
deadline. What will that be?
I'm planning to extend it until this week, Friday. Friday. Do you need more time? Should be fine, right? Friday should be fine. Okay.
I submitted mine yesterday, but I think I have some more.
Yeah. That's why I'm extending it because I don't want you to do any homework without listening the topic in the class or going through the problems in the class. That's unfair if I ask you to do the homework first and then listen to the topic. It's not good. We are just running one lecture behind. I'll try to compensate it in some other lecture. Any other questions? Any further discussions? Anything?
Ask about this.
Yes.
So the slight line angle and the voltage at us two are due to the losses.
Due to the losses. Line, because the line, we put 0.3, 0.6 R and L. So that's the inductive reactance that we put. So that inductive reactance is going to compensate some power factor to the line. So that's compensating it. Good question. So we can observe it. And the last part of the line, the diagram is saving. So when you are saving it, you have to save it as case and save it as case, and also you have to save it as one line. So if you want to save it, put it in the edit mode. Want to look at the one line diagram. If you want to navigate from this screen to one line diagram, go on the right here. Right of the window, open Windows. You can see here, Model Explorer, one line. Okay. Click one line, you will come to this. Okay. Put it in edit mode. Go here. Save case as well as save one line. You have to save both. If you save one, then when you reopen it, you will not get it. Okay. So it will save us two different PWD file and binary file, I think. So it will save us two different files and you have to save it. Every time you save, you have to save it like this. Save case and save one line. Okay. No, save case and then save one line.
Oh,
And name it so that you can, we are going to work on this, we are going to develop this diagram further. So save this one so that we can add more components to it and analyze the results. Okay. As we process through it. Right. Can I close my diagram?
How do you get back to the one from
Here, open Windows. You can see the one. How many screens you are opening? You can see here, open Windows. Under this, it will list down all the screens that you are opening.
I can see only two.
Have you done this analysis? When you put it in run
I
mode?
also only have one, but I closed the other. I closed that one.
Okay, you can minimize it. You can minimize it and you can close it. So that you will have only
So
one.
now you only have one.
Right. So I'm going to close it. So I have to save mine. So if I open the folder, I should be able to see both. You should be able to see both. Sample example, Powerwall binary and